Wait, did you know that companies like Amazon, Microsoft, and Google frequently use this exact problem to test your ability to handle pointers and cyclic data structures? Welcome to the ultimate walkthrough for LeetCode 141, the linked list cycle challenge. This is the fastest way to learn data structures and algorithms and your premium revision material for your next big interview. Let us look at the problem statement. Given the head of a linked list, we must determine if the list has a cycle in it. A cycle exists if there is some node in the list that can be reached again by continuously following the next pointer. We return true if a cycle exists and false otherwise. Imagine it like this: if you are walking down a straight road, you will eventually reach the end. But if the road loops back on itself, you will find yourself passing the same landmarks over and over. Think of two runners on a track. If one runner is twice as fast as the other, they will eventually meet again on a circular track. But they would never meet on a straight path unless they started at the same time. This is the core intuition behind our strategy, known as Floyd's tortoise and hurry algorithm. Our golden rule is simple: we use two pointers. The slow pointer moves one step at a time, while the fast pointer moves two steps at a time. If there is a cycle, the fast runner will eventually lap the slow runner and they will meet at the same node. If the fast pointer reaches the end of the list, we know there is no cycle. Now, let us dive into the dry run. This is the most important part. Look at our linked list on the screen. We have nodes with values 3, 2, 0, and -4. Notice that -4 points back to 2, creating a loop. Our tortoise and hurry tracker is at the bottom. We initialize both slow and fast pointers at the head node with value 3. At the first step, slow moves one node forward to value 2. Meanwhile, fast moves 2 steps ahead, passing 2 and landing on value 0. Since they are not at the same node, we continue. At the second step, slow moves one step to value 0. Fast moves 2 steps, first to -4, and then following the cycle arrow back to value 2. The gap is closing. At the third step, slow moves one node forward to -4. Fast moves 2 steps from 2 through 0, and also lands on -4. Look at the tracker, slow and fast are now identical. They have met at the same node, which means a cycle is confirmed. We highlight the meeting point in green and return true. This approach is highly efficient. In our Python implementation, we initialize both pointers to the head and use a while loop that continues as long as fast and fast.next are not null. Inside, we increment slow by 1 and fast by 2. If they ever equal each other, we immediately return true. If the loop completes, we return false. For complexity analysis, the time complexity is O of n, where n is the number of nodes, as we visit each node at most once in a single pass. The space complexity is O of 1 because we only use 2 pointers regardless of the size of the list. That is all for linked list cycle. Save this video for your interview prep and send it to your coding partner.